Alrighty, Muso here. Let's get into gravitational potential energy. So again, remember, you got to get all those other concepts still in there. You got work, your kinetic energy, all that stuff still is coming into play, but this is going to be more specifically to potential energy. And let me give you the equation first, and then we're going to explain why the equation is the way the equation is, and really how it's not really a new equation, okay? So the equation for gravitational potential energy, as we've already shown in the prior video, PE equals... By the way, it's PE due to gravity. Often it's important to put that G in there. You don't always have to. PE equals mgh. Now, especially at the AP level, a lot of times you see folks replace PE with the capital letter U. Don't let that throw you off. It's just another variable for potential energy, okay? I like to stick with PE because it just makes sense. PE is potential energy. Okay, PE is mgh. Now, let's use in a scenario here where I have the ground level and I have an object at the ground level, and I'm going to take that object and I'm going to lift it up to a higher spot. So here, h is 0. I'm going to take this object. I wish I had like a magic specific expo marker that I can just go red and it turns to red, and I just say black and it turns to black. It would make this whole making my diagrams multicolor a lot easier. Or I can just stick to one color, but I don't know. I don't want to. It doesn't look cool and pretty. Anyhow, I take this rock and I move it to a higher spot. So now I'm going to say h here is 10 meters. And just to help quantify this, because I've already started, I'm going to say the mass. And we'll say 10 kilograms. We'll make things easy, right? So I took this rock and I moved it to a higher spot. Now think about this. A force had to have been required to move it to that higher spot, right? How much force was required to move it, especially if I'm moving at a constant velocity? What's the force required? Well, think about it. Think about it. Think about it. What's the force required to get it to go up? Excuse me? Yeah, that force is the weight of the rock. Because there's a weight down of mg, it requires me, if I'm going at a nice constant velocity, to lift it with the same force. So, I did work on it, right? I know I did work on it because I gave it more energy. Remember, work is change in energy. In this example, that work will be change in potential energy. How much work did I put into it? Well, I put into it the amount of force I needed to give it times the distance parallel to that force. Well, if I'm lifting the rock up and it's moving up, they're parallel to each other, so I can ignore that parallel part. Well, what's the force I had to provide? I had to provide the weight of the rock, mg, and look at this, the distance it traveled is h. I'll be a little bit more specific. It's change in h because I'm giving it energy. Change in, what's changing in the mass? No. What's changing in gravity? No. The height. But isn't that fancy? The equation for potential energy, especially change in potential energy, is work. It's the same thing. I'm just being more specific here, okay, people? Let's not get too much into this. MGH really is MAD, G is A, H is D, and MA is really F, MGH is really FD. It's the same equation, just specific to height. That's all it is. Potential energy due to gravity is mg delta H. So in this example, how much potential energy did I give it? How much work did I put into it? It's 10 times, I'm going to round gravity to 10 just because I want to, and I'm going to make H 10 times 10 times 10. Yeah, 1,000 joules of energy went into lifting this rock, this 10 kilogram rock, 10 meters. Cool, right? How much work did I do then? Yeah, 10,000 or 1,000 joules. Did I keep saying 10,000? 10 times 10 times 10 is 1,000. 1,000 joules of energy to lift it 10 meters. That's really the nuts and bolts to gravitational potential energy. But I guess I probably should be a little bit more specific than that. So let's erase this. Let's get this diagram going here. Here's one thing you got to understand. This h value, it's always relative. It's relative height. Now, more often than not, we treat the h relative to the lowest possible point, which is the ground. But I do need you to understand that it can be relative to anything. Let's say I'm in my classroom. Instead of this being on the ground, this was on my surface of my desk. So this is the table. But that table itself is a certain distance above the ground, right? So maybe this is now the ground. I'm calling this 0. So I know that this object, if it's still that 10 kilogram object, it has PE of 1,000 joules, as I just did the math for, but that 1,000 joules in this new scenario is relative to the desk, not to the ground. So that reference point always needs to be defined. We need to know what it's relative to. What's it referenced to? Well, in this case, it's in reference to the desk. It's at a height of 0 at the desk line. Maybe this height down here is an additional 2 meters below the ground. So I'd say this h, I could probably say negative 2 meters if I wanted to. I could then say, yo, all right, that means it has PE of 1,000 joules to the desk, but it now has more than 1,000 joules in reference to the ground. My potential energy to the ground is mg delta h to the ground, which is 10 times 10 times 12, right? And so that'll be, 1,200 joules of energy. So there's an additional 200 joules above the ground. So if this object, ready for this? This is where we're going to do a little foreshadowing and conservation of energy, but might as well drop it on you. And drop it. Here we go. If I drop this object from this height and it falls to the ground, it's going to go from 1,000 joules of PE to right before hitting the tabletop, KE of 1,000 joules, as long as there was nothing lost to the environment. There was no energy loss. Or if instead of it falling to just the table and it actually was next to it and it fell all the way to the ground, how much KE would it have right before hitting here? Yeah, 1,200 joules. They're all connected, right? We're going from stored energy to moving energy at this spot. That's going to be the conservation of energy video. I don't want to ruin that video for you too much, although you can probably see where I'm going with it, right? Yeah, I've already shown you. Okay, I wish this is where I'd say, hey, any questions? Now, if this was like a live video session, you'd be able to chime in and I'd be able to respond, but it's not. I don't think you have any questions because I'm not hearing any. We're going to come back to gravitational PE in the other videos a lot more. Understand, once again, energy is scalar. Work was involved here. There's units of joules. PEG is mgh. I don't know. I don't think there's any more I've got to do here. I'm going to wrap this video up and I'm going to come back to PE in a future video. Cool. Thank you.